Okay, we'll go ahead and get started. Can the people on Zoom hear me and see my screen?
Yes. Yeah, we can hear you and we can see your screen.
Okay, thank you. Okay, so for those of you who took chemistry with me last semester, you know I'm Walter Gavlik and I'll be your instructor this semester. I know we have a few people who are new this semester, so welcome. And for the people who are new, as we go through, if you have any questions or anything, please let me know and I'll try my best to answer them. So the first thing we need to do is this first week of class, I need to take roll. And so basically, if you don't show up to class the first week, they drop you from the class. So it's important to show up and answer here when I call your name. So I'm going to go ahead and start that. Bola Akaniemi.
Here.
Was I closer this time than last semester?
Yeah, a little bit. It's Bolanle Akiemi.
Okay. Sorry, maybe I'll eventually get it.
No worries.
Addie Cascanet.
I'm here. I'm on my brother's laptop right now, so that's why it says John, but this is Adelaide.
Okay. Tony Sebahar.
Here.
Amber, I see you're there. Alex Fopp.
Here. Here.
Aaron Gallagher.
I'm here.
Addison Hanasek.
Here.
Nick Hunziker.
Here.
Heather Jones.
Here.
Isabel Llewellyn.
Here.
Brenda McDonald,
Here.
Vinnie Mojis, is that right?
Yeah, that's fine.
Oh, good. Jen Munger,
Here.
Cody Neal,
Here.
Shelby Patterson,
Here.
Copper Petermeyer,
Here.
Nathan Rivera,
Here.
Devin Schulstad,
Here. Here.
Katrina Solzwich,
Here.
Terry Spees,
Here.
Alexa Wagner.
Here.
Okay. Great, everybody's here, great. Okay. So, as you know, this is a continuation of the first semester of Gen Chem. So for those of you who were in the class last semester, it'll be pretty similar this semester as it was then in terms of the exams and quizzes and all that. But that said, I would like to go over and point out some things on the syllabus, and so that everyone is clear on some things. And part of this is just some questions that I got last semester that I probably didn't explain it well enough at the beginning, and so I want to make a little better attempt at that. So I'd like to spend a few moments just going through this. So some of this is just kind of boilerplate language, which is fine. You can take a look at when you get a chance. In this class, everything is posted on Canvas. So this syllabus is posted on Canvas. And the lectures are posted on Canvas. The other thing is the lectures are recorded, and there is a YouTube channel where you can listen to them again if you want to. And I'll post that information on the Canvas site as well about where to find that for the YouTube. As far as I'm aware, not many students look at it, but my family takes great delight in watching and listening to some of them making fun of me later. So it does serve a purpose. So my office is still ISB 333, so that's the building next door up on the 3rd floor. If you need to talk to me about something, or if you're struggling with the class or something like that, I would encourage you to send me an email and we can set up a time to talk. I teach every morning, but the only afternoon that I teach is Thursday afternoon. So the other afternoons, I'm usually pretty available if you need to talk about something. We have some of the things that are going to be done in the class here. You can take a look at that. As I said, things are posted in Canvas here, you see under materials. So just as last semester, because of the nature of COVID and the Zooming and all that, the exams and quizzes will be given through Canvas once again, as we did last semester. So be sure and check Canvas periodically for this class. The textbook is the same as last semester. So if you bought the textbook last semester, you'll use that again here. In terms of grading, we have 5 quizzes and we have 5 exams plus a final exam. And just as last semester, you get to drop the lowest grade of the quizzes that you have and the lowest grade of the exams. Now, the exam drop can't be the final, but of those 5, you can drop the lowest. I did have some people send me messages saying, I want to drop this particular quiz or this particular exam. Just so you know, I automatically go through and look at the quizzes that you take and drop the lowest one. So you don't have to let me know that. I'll do that automatically, same with the exams. The other thing I want to mention about that is, if you miss a quiz or exam for some reason, whether you're sick or forgot about it or didn't study and don't want to take it or whatever, then that will count as your drop. Okay. If you miss more than one, then those additional ones you miss, you will get a 0 for, because there aren't makeup ones. Now, if you know something is coming up and you talk to me ahead of time and we work out an agreement on something, that's a different situation, and that is possible if someone has something. I mean, the sports have been kind of weird this school year because of COVID, but in the past, sometimes people who were involved in sports or some other activity where they know well in advance they're not going to be around for that, then we can work something out. So, but unless you let me know that well in advance, the expectation is you'll take the exam or quiz. And once again, just like last semester, the quizzes and exams have a time component to it. Okay, and that's part of the idea of building the test, is to make it a bit challenging from a time perspective. So be aware of that. Here's the grading scale. You can take a look at that and look through that. Some university policies in terms of dropping and withdrawing, academic honesty, things like that. And the one I want to point out is the special services one. So if you have some reason for an accommodation, you're entitled to that, but you can't just tell me. You have to go through call the number here and go through the process. And the way that works is after you work with those people, they'll send me a letter, and then it's all confidential, but they'll send me a letter and then telling me what the accommodation is, and then I'll honor that. So if you do fall into that category and you haven't done that already, you need to do that before with the first test or first quiz. Okay, so just talking about the remote learning a little bit. So because of the COVID situation, we're offering this class both remotely and in person. I love seeing your faces here. It makes it much easier to lecture when there's people to interact with. I'll tell you that right now. So thank you for the people who are here. But I realize not everyone's comfortable with that, and so that's fine. So we have this remote option. The exams and quizzes will all be remote. So you can come in and take them the exams. The quizzes, you can come in and take here in the room as well if you want. But they are open book, open notes, all that kind of stuff. And so that's one reason for the time factor. So you don't have enough time to just look everything up, hopefully. You have to know some things, and you can look some stuff up, but I don't want you just looking stuff up. The other thing I want to point out is the expectation is that you're taking the quiz or the exam by yourself. So you're not in a group of people sharing work or anything like that. If you do that and you get caught, that is considered cheating, and then there's an appropriate path forward on that. So I just want to remind everyone of that. So there is a bit of an honor system here. Excuse me. So one thing I want to point out is if you're in the class and you're going along and you're having some problems, you don't understand something, or you're struggling with your grade or something like that, please contact me and we can talk about it and see kind of if there's anything that we can do to help you get back on track. What I don't want is, I don't want you to just struggle in silence. The goal is for everyone to have a nice experience, a good experience in the class, and everyone be as successful as possible for them, okay? That doesn't mean everyone's gonna get an A, but I want people to be as successful as possible. So if you're putting in some effort and doing some work, you should be able to get through this class. And that's the expectation of mine, and should be your expectation also. So if you really are struggling, please come and talk to me. So in terms of what we're going to be doing this semester, the goal is to cover these 11 chapters. Last semester we covered 10 chapters. So we'll see, we'll start and we'll go. And if we need to go a little slower or faster, we'll adjust accordingly. But this in the syllabus is the first attempt at kind of giving you a feel for the timing of what chapters we're covering when the quizzes are, when the exams are. So 5 quizzes and 5 exams in 15 weeks is a lot. That is intentional. The idea is that you have the tests that usually cover 2, sometimes 3 chapters, but you'll have a quiz on one of the chapters before you have the exam. So the idea is that you'll get a feel for what the tests are going to kind of look like on that quiz. You'll have studied for that chapter some. And so then when you take the exam, you don't have to study it quite as much because you've already done some of your studying. So rather than saving it all up and then you got to study a whole bunch of stuff at once, the idea is to have a lot of opportunities to get points. So I would just remind everyone, and I think the people last semester probably saw this by the end of the semester, but especially for the new students, is by having a lot of quizzes, a lot of exams, there's a lot of opportunities for points. The drop of one of each of those means that one bad day doesn't sink your grade. And so I would just say it's a marathon, not a sprint. So you don't want to get too excited if you do real well on the first exam or quiz. You don't want to get too sad if you do bad on the first one. Okay, keep it in context of it, it's a long semester. So today we're going to start with chapter 11 and we'll cover that this week. Next week we'll start on chapter 12 and then next Thursday we'll have our first quiz. So it'll come up pretty quickly. Okay, the other thing I wanted to mention is I haven't heard to the contrary. So as far as I know, in mid-March, the week of March 8th, we are scheduled to have spring break. And that's the stuff in green there. So last semester was a bit odd because we didn't have the fall break. They cut that out so they could squish the semester together a little bit more. As far as I know, we still have the spring break. So hopefully that will occur. And if it is, then we'll have that week off. So those were the main things I wanted to point out about the syllabus. You can take a look at it. Like I said, it's posted on Canvas. You can take a look at it in more detail if you want. And if you have any questions, let me know. I do have one bit of information that I want to share with you that's sad news. Some of you had Professor Nemani last semester for Gen Chem Lab. And I'm sorry to say that he passed away December 17th. So those of you who thought you were going to have him this semester, obviously you're not. And so they had to shuffle do some instructor assignments for the lab. And so that's why he's not going to be maybe who you thought you were going to have this semester. So, okay. Any questions before I start on chapter 11? Okay, in chapter 11, we're going to talk a little bit about liquids, but the big thing that we're talking about are intermolecular forces. So when I say intermolecular forces, does anyone have an idea of what I'm referring to? Any thoughts on that? So when I say intermolecular forces,
is that the force between molecules?
it is very good. Force between molecules. So last semester, we talked about bonding. Remember, we talked about covalent bonds and ionic bonds and things like that. That's intramolecular forces. So that's how things are kind of interacting within the molecule. Intermolecular forces are when you have a bunch of molecules around, how do they interact amongst themselves? So that was good. And so the interesting thing about intermolecular forces is that intermolecular forces are really what give us a lot of the physical properties of compounds and solutions and things like that. So we're going to talk about what kind of goes in to this thinking. So in this example, we have HCl, hydrogen chloride. And what we see is we see the hydrogen bonded to the chlorine. That's a covalent bond, and that's an intramolecular attraction. So intra means within the molecule. So that's within the molecule, we have this bond, in this case, a covalent bond between the hydrogen and the chlorine atoms. We see here that we have an interaction between the hydrogen and the chlorine of the other molecule. That's a weaker interaction, but that's an intermolecular attraction. So the bonds are always going to be strong, okay? So that those interactions within the molecule are going to be stronger. But the intermolecular attraction is what gives some of the physical property information. And here we have some examples: boiling point, melting point, viscosity, surface tension, capillary action. And we'll talk in a little more detail about what each of those things are and kind of why intermolecular makes a difference for those. But the things we want to remember here are intramolecular is the bonding within the molecule, and intermolecular is that interaction between molecules, okay? And the intra, the bonding is always much stronger than the intermolecular between the molecules, but it's that intermolecular attraction that gives us some of these physical properties. So if you remember before, we talked about 3 states of matter: gas, liquid, and solid. So let's just kind of review what that means again. So with gases assume the volume and shape of the container. So whether your container is little or big, you put a gas in, it will expand or contract to whatever the size of the container is. Liquids will follow the shape of the container, but they don't expand or contract. And then solids, they don't do anything. If you have a solid and put it in a small container or a big container, that solid doesn't change. It doesn't get bigger or smaller. And so the other thing about gases is that you can compress them. You remember last semester we talked about pressure and we did some calculations around pressure and things like that. That's an example of compressing things by changing the pressure of the gas. Liquids really don't compress usually. Solids usually don't compress either. So that's a distinction between the gas and the liquid and the solid phases. Gases flow real easily. Liquids flow pretty easily as well. Here it says solids don't flow. That's sort of correct, but you can make solids flow. The example I always think of is if you have sugar. You have sugar and you want to pour some into your coffee or tea or whatever, that pours, so it does flow. But from a normal perspective of flowing kind of on its own, it doesn't. And then one of the big things is when we talk about diffusion, diffusion within a gas happens pretty quickly. Diffusion within a liquid is more slowly. And one way you can think of that liquid is if you had, say, a glass of water and you put a drop of dye in it, you could kind of watch it diffuse with time. That doesn't happen real fast. That's why I usually stir stuff up to get that diffusion to go more quickly. Gases occur pretty quickly when you have that diffusion. And solid diffusion within a solid, that's really slow. So when we talk about these three states of matter, gas, liquid, and solid, the difference, the fundamental difference of why you have a gas, liquid, or solid are those intermolecular forces of attraction. So you think about when we talked about gases in the past, you got the molecules, they're all spread out, they're not real close to each other. So if they're not very close to each other, they really can't have attraction, and they're far away because they didn't attract much and stay together. So with gases, limited attraction between the molecules or the atoms, and then you have some distance as well. With liquids, you start to get more of an attraction, okay? And so you get the attraction, but you don't get as much as what I would call a locked-in attraction. With the solids, things get packed together more closely, and there's usually structure to that packing. And in a couple chapters, we'll talk about that structure. And so you get that structure because of the attraction of the molecules to each other. So those intermolecular forces are more strongly in that solid matrix. So liquid, things can be pretty close together, but it's more of a randomness to it. The solids, there's that more structure. So when we talk about intermolecular force, and here we're talking about neutral molecules, so in other words, no charge, there's three types of forces that we talk about. The first one is dispersion forces, sometimes called London dispersion, sometimes induced dipole-dipole interactions, but we'll just refer to it typically as dispersion forces. The second one is dipole-dipole forces. Does anyone remember what we mean when we talk about a dipole? So last semester, we talked about how some elements are electronegative. And so what that means is they like to attract the electrons in the bonds. So you have a bond, and it's not an equal sharing of those electrons. Some of the electrons go towards one of the atoms a little bit more, and that atom is considered to be electronegative. And if we had a periodic table in front of us and we were looking at it, we would say the elements in the upper right-hand corner, those are the ones that are more electronegative. So something like fluorine, for instance, is pretty electronegative. So that means if fluorine is bonded to something else, there's a pretty good chance that it's going to be the most electronegative atom in that bond. And so the electrons are going to be a little bit more over towards the fluorine and less on the other atom. And that means the fluorine will have this kind of pseudo negative charge to it, and the other atom will have a partial positive charge. So that kind of shifting of the electron density that's what we call forming a dipole. And so dipole-dipole interactions between molecules, that can lead us to some of these interactions, these intermolecular interactions. And then finally, the third one is another type of dipole-dipole interaction that we call hydrogen bonding. So that's a bit of a misnomer because it's not a real bond. It's not like a covalent bond or ionic bond or something like that. So it is an interaction, and it's not an intramolecular interaction, it's an intermolecular action. So even though we call it hydrogen bonding, it's not a true bond. And we'll talk a little bit more about why it's called that in a little bit. So those first two types also are often referred to as van der Waals forces. So a lot of times people either talk about van der Waals forces or hydrogen bonding and kind of leave it at that. The hydrogen bonding, like I said, we'll talk in a little more detail in a few moments. That's really important. That's one that, especially if you go on and take organic chemistry, you'll hear a lot about hydrogen bonding. Hydrogen bonding is kind of a big deal in reaction chemistry and things like that. So when we talk about those attractions, whether it's intra or intermolecular, we said that the intramolecular, so the bonding is much stronger than the intermolecular forces. And so here's some examples to illustrate that. So we see in this table, we see some examples of ionic bonds, metallic bonds, and covalent bonds, and then the substances associated with that. And we see melting points and boiling points. These are all in Kelvin, and we see pretty big numbers. Then we go down here to the intermolecular forces, and we have dispersion forces, dipole-dipole interactions, and hydrogen bonding. And we see much smaller numbers in terms of the boiling and melting point. And you think about when we're talking about boiling point and melting point, what are we doing? We're putting energy in, right? Last semester when we talked about these, you got to put energy in to make something boil or melt or things like that. So if you got to put a lot of energy in, as indicated by these high temperatures, that means it must be pretty strong what you're trying to disrupt to cause that change. And so this just further illustrates that the intramolecular, the bonds, the actual real bonds, are much stronger than intermolecular forces. So that's the takeaway here. And we just want to remember, once again, that even though we're calling this hydrogen bonding, it's not a real chemical bond. Okay, so don't forget that. Like I said, it's kind of unfortunate they call it hydrogen bonding, but it is what it is. And so we just want to remember that that's not a real bond. It's not like a covalent bond or anything. So when we talk about dispersion forces, there's a term called polarizability. And so if you have a non-polar particle, non-polar molecule, you can do things to it to get it a little bit of shift of the electron density. And that's called polarizing it. And so by distorting that electron cloud a little bit, you can get a little bit of a dispersion force created, okay? To be honest, in nonpolar, things like that, you can do it, but that's a much weaker force than either the dipole-dipole or the hydrogen bonding, okay? And the reason for that is dipole-dipole interactions and hydrogen bonding interactions, those are there all the time. Those occur by nature of the molecule and the arrangement of the atoms. This one, with the polarizability, you got to do something to it to get this kind of slight shift in the electron density, electron cloud. So it's not as strong. So what are some of the factors that influence the polarizability or that dispersion force in a molecule? Well, one thing is the number of electrons in an atom or molecule. So the more electrons you have, the more dispersion force you can have. Another thing, size of the atom or the molecule or the size of the molecular weight. So the bigger it is, the more polarizability it can have. And that kind of makes sense because if it's bigger, there's probably more electrons associated with it. And then finally, the shape of the molecule, when you have molecules that have similar masses, the more compact it is, the less dispersion force. And so let's just talk about that for a moment. When we talk about shapes of molecules, we know that there's something called an isomer. And we said before that an isomer is something that has the same molecular formula. So in other words, the same molecular weight, but the atoms are arranged differently in the molecule, so the shape is different. And so here we have two examples of that. We have pentane, N-pentane. The N means it's a straight chain hydrocarbon. Okay, so it means the pentane is just 5 carbons in a row in a straight line, and that's what they're kind of representing here. The white things are the hydrogens, and then the other ones are the carbons. And then down here, we have neopentane, and that's more of a branch type of pentane. So you have 5 carbons there, but they're kind of globbed together. It almost looks like a ball. It's not a ball, but it kind of looks like it. And so what this means is, because this one on the bottom is kind of masking some of the potential areas that you could have dispersion force type interactions, you're just not going to have as much available. Whereas in the pentane above, that being nice kind of laid out, there's more opportunity to have some of those interactions and to have some of that polarizability and things like that. So the thing, once again, the things that affect us in terms of polarizability, and when we say polarizability, we're talking about that dispersion force. When we talk about all this stuff, we're talking about the ability for those molecules to kind of interact with each other. And number of electrons in the atom molecule, the more electrons, the more dispersion force. Size is important. So the bigger the molecule, the bigger the molecular weight, polarizability increases. And then finally, if the masses are the same, so remember, if the masses are the same, the electrons will be the same, the size will be the same, but that orientation then comes into play. And the ones that are a little more bunched up are going to have lower polarizability. And so when we look at these two, they give us the boiling points. So the pentane, N-pentane is 309.4 K, and the more bunched up one is 282 Kelvin. So we see an example of that. They're the same size, right? So they're going to have the same number of electrons, they're going to have the same molecular weight, but because of this orientation of how the different atoms are attached together, this has less of a dispersion force. And so if it's less of a dispersion force, we put less energy in to make whatever it is going to happen. And so in this case, we have a lower boiling point for this one than for the N-pentane. Does that make sense? Okay. This is another example of that linkage between polarizability and boiling point. Once again, the higher the polarizability, the higher the boiling point. So if you have more of those intermolecular forces, that's what we're talking about with polarizability, then the boiling point is going to be higher, given the kind of the conditions we talked about. So larger molecular atom, higher molecular weight, larger size, more electrons, all those things lead to higher polarizability and higher boiling points. So let's go back and revisit dipole-dipole interactions, because now, you know, some of that polarizability on the nonpolar molecules and that, it's there and it has, but in the scheme of strength, it's the weakest of all the interactions. And so let's look at dipole-dipole interactions. These are pretty common, and these once again, remembering what we talked about when we talked about what are we doing when we say something has a dipole. We said that that's where there is, with polar molecules, we have one area that's a little more positive and one that's a little more negative because of how those electrons are shared in the bonds. And so we talked in the past about how to determine if a molecule is polar. That's where we look at that electronegativity chart and think of, on the periodic table, upper right-hand corner is more electronegative. So if you've got some of those atoms that are in the upper right-hand corner, you probably have a polar molecule. And so we talked about a dipole, and dipole literally means two poles. And that's when we talk about a little bit of negative, a little bit of positive in terms of that electron sharing. And so in polar molecules, we have a permanent dipole. And so we call it a dipole moment because it has that plus and minus charge distribution, but it also has a magnitude to it. And so that's why we call it a moment. And so some things are more polar than others, have a higher dipole than others, things like that. So, but in polar molecules, it's not something that's induced. It's there all the time by nature of the atoms that are involved in the bonding and the arrangement and all that stuff. And so in these situations where you have polar molecules, you can have some interactions. And here we have two, at the bottom, we have two examples. We have CH3CN, and we see on the left there, we see an attractive dipole-dipole interaction. So any ideas what an attractive one would be? In the past, we talked a lot about in chemistry, opposites attract. Okay, you know, you hear that sometimes with people who say, oh, they like each other because opposites attract. Well, that may or may not be true with people, I'm not certain, but in chemistry stuff, it definitely is. And so in this case, what you have is you have these molecules which have a permanent dipole. So in other words, you have that shift of the electron density. So you have some portions of the molecule that have a positive type, so they're a little electron deficient, and you have some portions of the molecule that have attracted the electrons and have a little bit more electron there. So that's where you get the partial negative and partial positive charge on the molecule. Well, the partial negative of one molecule is going to match up with the partial positive on another molecule. Okay, so that would be this one on the left here, the red bonds that they show. There's also a repulsive component of that. And on the right side, there's some blue bonds, dotted things. You shouldn't say bonds, but interactions. And that's where you have a negative end, one molecule, kind of matched up with a negative end on another, or a positive and a positive. In that case, that's going to be repulsed. Okay, that's not going to attract. So with these dipole-dipole interactions, you can have either the attractive ones, where you have a negative with a positive, or you can have the repulsive ones, where you have two negatives or two positives. And so that factors in also in terms of the strength of things and stuff like that. It gets a little more complicated when you have bigger molecules. When you have small molecules, it's a little easier to see. When you get to the bigger molecules where there's portions that are nonpolar and polar and this and that and all that, then it really gets kind of complicated how they interact with each other. So let's talk a little bit more about the dipole-dipole interactions. So we have a series of compounds here from propane all the way to acetonitrile. And acetonitrile is the one we had just looked at a little bit. And so we look at the first one, propane, CH3, CH2, CH3. Is that a polar molecule? Any ideas? People in the class get picked on, so sorry. You think that's polar? Yeah.
No,
Why don't you think it's polar?
because there's no charged ends.
Well, that's sort of right. It's more, if you think back, if we could, too bad we don't have a periodic table in there. If we thought of the periodic table, there's none of those ones in the upper right-hand corner. There's no oxygen, there's no nitrogen, there's no fluorine, there's none of those in that molecule. And so because of that, we don't really have anything that really wants to pull the electrons, okay? And so that, by definition, then tells us it's nonpolar. Then we go over, and the ether, we start to introduce some polarity in there because of the oxygen. Acetaldehyde, a little bit more, with that double bonded O in there. And then finally acetonitrile with that cyanyl group, the C triple bonded to the nitrogen. That's where we start to get some polarity going on. And so as we go here from propane up to acetonitrile, we're increasing in polarity. If we're increasing in polarity, that means we can have more dipole-dipole interactions. In that first one, we're not going to have any dipole-dipole interactions. We might have some of those van der Waals type forces type things in the beginning that we talked about, but those are pretty weak. And if you look at that propane, boiling point's 231, but that's a Kelvin. So that tells us at room temperature, it's a gas. And propane is what, if you have a gas grill, that's what you use to cook with. So you know that's a gas. Acetonitrile is typically a liquid, is its most common. And so you see its boiling point is up at 355 Kelvin. So at room temperature, it's not a gas. And so the reason for that is more polar has more of these dipole-dipole interactions. And so these molecules, if you look at their molecular weights, we have 44, 46, 44, 41. They're about the same. So it's not, the difference isn't because one of them is bigger. Okay, because remember we said that was one of the things that could influence the interactions was size, and that size impacted boiling point. But here, size can't be the answer because they're all about the same, all right? And so what's different though is that polarity of it, with acetonitrile being the most polar molecule. And because it's the most polar, we have more of those dipole-dipole interactions. And that's what kind of holds the acetonitrile together and doesn't hold the propane together. So then the propane is pretty easy to have propane gas. Kind of difficult to have acetonitrile gas. So which has a greater effect, dipole-dipole interactions or dispersion forces? Well, those dispersion forces are definitely weaker than dipole-dipole interactions. And that's because the dipole-dipole interactions are sitting there all the time. It's pretty well established. The dispersion forces aren't as strong, aren't as established. But the disclaimer on that is, if you have a really big molecule that doesn't have dipole-dipole interactions, and you have a small molecule that has dipole-dipole interactions, in other words, it's polar, the one with the dispersion forces also could be stronger just because it's so big and it's like a lot of strength in numbers type thing. So on a one-on-one basis, the dipole-dipole interactions are always a stronger interaction. But for the dispersion forces, if you have enough of them, this is where that being a real big molecule can maybe overcome a small molecule's dipole-dipole interaction. But for the most part, you would say dipole-dipole are stronger than dispersion. Okay, hydrogen bonding, let's talk about that for a bit. So hydrogen bonding is dipole-dipole interactions, okay? It just gets a special name because it always involves hydrogen. That's why it's hydrogen bonding. And then also, it's always associated with one of these three electronegative elements. So nitrogen, oxygen, or fluorine. And so in dipole-dipole interactions, the hydrogen needs to be bonded to one of these three elements. Okay, we have some examples here. The first one, we see hydrogen's bonded to oxygen. Then we have hydrogen bonded to fluorine, bonded to nitrogen, oxygen again with nitrogen, and then a nitrogen and a hydrogen there. So what we have is, we have a covalent bond of the hydrogen to one of these electronegative atoms, okay? Because oxygen, fluorine, nitrogen are much more electronegative than hydrogen, when we think of that dipole, that nitrogen, oxygen, or fluorine is going to have a partial negative charge because it's going to pull that electron density its way in that covalent bond. And then the hydrogen is left with that partial positive charge. What can happen then, and this is where the hydrogen bonding comes in, is the hydrogen then, because it's looking for electrons, it can have an intermolecular force attraction to the oxygen, the fluorine, or the nitrogen, which now has a partial negative charge to it. Okay, and that is what we're calling the hydrogen bonding. Okay, it's not the hydrogen itself within the molecule. It's not the intramolecular. It's the intermolecular association. And of these like dispersion force type things, hydrogen bonding is the strongest one. And that's another reason why they kind of break out the hydrogen bonding based dipole-dipole interactions from the regular dipole-dipole, because the hydrogen bonding is usually stronger. So once again, you have molecules that have covalently bonded hydrogen to either oxygen, fluorine, or nitrogen. You create that dipole there where the oxygen, nitrogen, or fluorine will have that partial negative charge. The hydrogen will have partial positive charge. And then you have an interaction between molecules. So this is that intermolecular attraction. So you'll have the partially negative part, and this, for the first example, that's the oxygen, and that'll be attracted to one of the hydrogen atoms. And you have that hydrogen bond intermolecular forming there. Okay, once again, it's not a real bond. It's not like the covalent bonds or things like that. That's why you'll see it drawn like this a lot of times with the dots. You won't see the straight line. That straight line tells you it's a real bond. This tells you it's an intermolecular force. It's an attraction, it's an association, however you want to think of it. What's interesting down in the last two examples, so the first three are just all the same stuff, okay? Water, HF, ammonia. But down at the bottom, we have ammonia and we have water, okay? And what you see here is you see this attraction of the nitrogen on ammonia and one of the hydrogens on the water molecule. On the bottom, same thing. Hydrogen, another one of the hydrogens from the nitrogen attracted to the partial negative charge of the water. So you have those last two is interesting because it's the exact same combination, but you see different associations because you have dipoles going on in the water, you have dipoles going on in ammonia here, you have hydrogen bonding in each, And so you've got these different interactions. So you can see how the interactions can get kind of complicated pretty quickly, even with kind of a simple system like that. I'll say it one more time, hydrogen bonding is a big deal. You know, we're going to touch on a little bit in this class, but if you go on and take organic chemistry or more chemistry classes, you'll hear about hydrogen bonding quite a bit. So this is, you know, sometimes the stuff we talk about in here, maybe you'll use it again if you continue on in chemistry, maybe you won't. Hydrogen bonding is one you definitely will. Any questions about the hydrogen bonding from anyone on the Zoom or in the class? Okay. So here's just a little more detail on that, kind of a repeat of what we've been talking about. But once again, we see on the bottom here, if you remember, this is one way we talked about we could draw dipoles, is the plus on the arrow is the positive portion. The arrow goes in the direction of the negative portion. And so this is what we talked about. We talked about how that electronegative atom will attract the electron cloud closer to it, so it'll have a little more electron density around it. Then it'll be partially negative. The hydrogen will be partially positive. And so then the other interesting thing about the hydrogen, as you recall, it just has the one proton. And so it doesn't have inner electrons. And so it's easy to kind of pull, and then it's really looking for stuff, right? So it's the idea of having a bond of the electronegative atom to hydrogen, and then creating that dipole, and then having some interaction there. That's the whole idea behind this hydrogen bonding. So one thing I just want to mention a little bit, which I think is interesting, is when we talk about density and intermolecular interactions and things like that, water's kind of an interesting one, because if you think about it, you know, if you ever drive by a lake or something and it's really cold, it's not uncommon to see ice on the top. So to me, it's interesting that ice floats on water. And that's because it's less dense. Because normally when I think of solid things, I think of them being more dense than liquids. But in the case of water, it's the exact same material, right? It's not like a different compound or something. When it freezes, it actually is less dense than liquid water, and that's why it floats. The other example, and I like this picture that we have on the slide here, we have, it looks like an old soda bottle filled with water. And we see it in liquid form, but then when we freeze it, and you've probably experienced this, you take a water bottle and freeze it, it expands, right? If it's too full, it might crack the bottle or something. I know that's happened to me before. And so once again, that's this, in this case, it's less dense, but it takes up more space, okay? And that gets down to some of this bonding stuff here, okay? So our covalent bond, that's the hydrogen to the oxygen, is 1 angstrom, but the hydrogen bond is 1.8 angstroms. And so as you get some of these formations here, it kind of spreads stuff out, makes it less dense, makes it farther apart, so the molecules get farther apart because of the hydrogen bonding. And that's why it floats. That's why it expands, because of that interaction there. Okay, let's talk about ion dipole interactions. So if we have a polar molecule and we have an ion, we get interactions. And so if you think about the ions, in this example, we have chlorine, or the chloride ion and sodium ion. So these other things around it are water molecules. So the red is oxygen, the two white things on it are the hydrogens. So what you see here is the cation, the sodium, down at the bottom, that's attracted to the partial negative charge. So it's attracted to the oxygen. The chloride ion, which is negatively charged, that has an interaction with the positive part of the water, which is the hydrogen ions. And so what this does is that this attractive force on the cation and the anion, that allows you to dissolve ionic compounds in polar solvents. And water is a very polar solvent. And if we look at this sodium and the chloride, well, we know sodium just doesn't come by itself. Sodium plus doesn't come by itself, and Cl minus doesn't come by itself. It's got to be part of an ionic compound. Anybody know what sodium chloride is? Sodium chloride is table salt. Yeah. So you do this all the time. You take salt and you put it in water and you dissolve it up, right? So this is what's going on when you do that. The chloride ion, the Cl minus, is interacting with the positive portions of the water molecule. The sodium plus is interacting with the negative portions of the water molecule. And that's how you get that dissolved. And that's why ionic compounds like sodium chloride dissolve so well in water, okay? Because water is a polar solvent. It's got dipoles going for it. Those dipoles, the charge on the dipole can interact with both the positive ion and the negative ion, just depending upon which end of the molecule it associates with. Okay, let's talk a little bit more about review a little bit these intermolecular forces. So we talked about dispersion forces. Okay, that was the first one. We can find that in atoms, we can find that in non-polar molecules, polar molecules, hydrogen bonding molecules, ionic solids dissolved in polar liquids. It's everywhere, okay? It's not real strong, but it's very prevalent. We look at the dipole-dipole interactions. Those have to be something that's polar, okay? And whether it's the ones that have hydrogen bonding associated or not, what is common is the molecules have to be polar so that we can have that dipole form. And remember, to be polar, that links us back to the electronegativity and having that sharing of the electrons in the bond, having them shifted a little bit more to one atom than another, and creating that kind of partial charge imbalance. Then we have hydrogen bonding. That needed our rules of we have to have hydrogen bonded to oxygen, nitrogen, or fluorine. And then that hydrogen then goes and has some kind of interaction with another molecule. And then finally, the last one was ion dipole interactions, where we're talking about ionic solids dissolved in polar liquids. Usually we're talking about water. So everything has dispersion forces. The reality is the strongest force tells us really what's going on. So if you have dipole-dipole or hydrogen bonding or ion dipole, that's gonna override and be more influential than the regular dispersion forces. So really, the way to think of it is, if you have atoms and non-polar molecules, it's really dispersion forces. If you start getting into polar molecules, then it's either the dipole-dipole or the hydrogen bonding. So when you have two molecules and they have similar masses and shapes, the dispersion forces are going to be about the same, okay? So you don't have anything, that kind of makes sense. If two things are pretty much the same, the forces should be pretty much the same. When you have two molecules with real different masses and there's no hydrogen bonding, then the dispersion force determines the substance with stronger attractions. And so that's where you have to go and look and see what properties you have with the molecules. Okay, what I'd like to do now is spend a few minutes reviewing a couple homework problems. So here's some homework problems I'd like you to take a look at. The homework answers are all posted in the Canvas under the homework section. So you have to see my handwriting, which isn't the greatest, but at least you can see what I did. But I would like to select a few of these and go through them with you just to make sure you're comfortable with them. But before I do that, any questions on anything we've talked about so far? Okay. Okay, the first one I'd like to take a look at is 1117. Describe the intermolecular forces that must be overcome to convert these substances from liquid to gas. So the first one is SO2. And so when you get a question like this, the first thing you want to do is try and figure out, is it polar or not? So a sulfur with 2 oxygens on it, do you think that's polar? Remember, we said when we were talking about hydrogen bonding that oxygen, nitrogen, fluorine, that really contributed to there being polarity there, right? So here we've got a couple of oxygens on a sulfur, so it's a pretty good guess that that's going to be a polar molecule, okay? So once we know it's a polar molecule, and we're trying to figure out what forces are really impactful, the most impactful one is going to involve a dipole, right? Because we said dipole is stronger than those regular dispersion forces. So they're there, they're always there, but the dipole is going to override. So now we just need to decide, is that dipole or is it hydrogen bonding? What do you think? Hydrogen bonding? How many think it's hydrogen bonding? Anybody? Why not?
There's no hydrogen.
There's no hydrogen, right? Don't make it harder than it is. It can't be hydrogen bonding if you don't have hydrogen. So that tells us that one's dipole-dipole interaction. The next one, CH3COOH. So it's acetic acid, and so there, is that a polar molecule? Yeah, it is. Once again, we see those oxygens there. That's usually a tip-off that there's some level of polarity to it. So now that it becomes, we think it's a polar molecule, then it just, is it dipole-dipole or is it hydrogen bonding? We've got hydrogen, right? So that's step one. Step two is, what's the hydrogen bonded to? In this case, the hydrogen is bonded to an oxygen. And that was one of the things we said we had to have, right? One, we had to have a hydrogen. Two, it had to have hydrogen bonded to either oxygen, nitrogen, or fluorine to be a hydrogen bond type situation. So this tells us that for this one, those hydrogen bonding interactions are going to be there. We're going to have some dipole-dipole, we're going to have some dispersion, but hydrogen bonding is the biggie for that one. Because remember we said we always have some of that other stuff, but it's the strongest one really is the one you worry about. And then finally, H2S, hydrogen sulfide. It's polar and it's covalent. So we can have dipole-dipole interactions. Do we have hydrogen bonding here? We've got hydrogen. Any, what do you think?
No, it's not.
Yeah, it's not, the hydrogen's bonded to sulfur. That wasn't one of the ones we said we needed to do that. So in this case, it'll be dipole-dipole interaction, not hydrogen bonding. So does that make sense how we go through that kind of logic to figure that out on these? Okay. Let's look at 19. So in 19, they give us a series of compounds, and they want us to list them in order of increasing polarizability. So we look at these compounds, and we know that polarizability increases as the molecules get bigger, right? As the molecular weight goes up. So for these numbers you see below the compounds, those are the molecular weights for each of those compounds. So we go from 16 all the way up to, I guess that's 393. Once again, the poor handwriting causes problems. So what that tells us as we go from methane, which is CH4, up to GeBr4, not certain what compound that is, the polarizability increases and the molecular weight increases. So the next part of the question is, it asks us about boiling points. So if the polarizability increases, what does that mean? That means those intermolecular forces are stronger, right? So the intermolecular forces for GeBr4 are stronger than for CH4, okay? And so what that tells us is then the boiling point should go the same way, right? If those intermolecular forces are stronger here than down for CH4, then that tells us that they're sticking together a little more. We have to put more energy in to break that and get it to boil, essentially. So methane, CH4, well, that's a gas at room temperature. So that further supports what we are. These other things, I have no idea what they are, so I don't know what those are normally, but methane is. So this goes back to these intermolecular forces telling us stuff about boiling point. Okay, let's look at 1125. What atoms must a molecule contain to participate in hydrogen bonding with other molecules? What did we say? We said you have to have hydrogen, right? And it's got to be bonded to fluorine, oxygen, or nitrogen. That's our definition of saying if something can hydrogen bond. First of all, we got to have hydrogen. That makes sense. And second of all, the hydrogen has to be covalently bonded to one of these other atoms. Then the second part of the question is they give us a series of molecules and want to know if you can have hydrogen bonding. So CH3F, I say there no hydrogen bonding. Why is that? We got a fluorine, we got a hydrogen, what's the problem? The problem is the fluorine isn't attached, isn't bonded to the hydrogen. It's bonded to the carbon, okay? And so we need that hydrogen and fluorine bonded to each other for this to work. So there's no hydrogen bonding there because we don't meet this thing that we talked about in A. In B, we have CH3 and H2. And so in that case, we're saying we have hydrogen bonding. And that's because when we write it this way, what this means is these two hydrogens were bonded to the nitrogen. Okay, so that meets our requirement up here of having hydrogen bonded to a nitrogen. The third one, CH3OH, that's methanol. And so once again, we have a hydrogen bonded to an oxygen. So there's that alcohol group, that OH group. And so because the hydrogen is bonded to the oxygen, we meet our requirement that we talked about in part A. And so we can have hydrogen bonding. We look at the last one, CH3Br, we say no hydrogen bonding. That looks similar to what we did on our first one, right? Where we said the fluorine was bonded to the chlorine. Here, the bromine is bonded to the chlorine. So bromine's electronegative too. You don't see it a lot, but it is electronegative, but it's not bonded to any of this stuff. It's not bonded to the hydrogen. Okay. Any questions about the couple of problems that I just went over? Okay, so take a look at those other homework problems, just to kind of give yourself some practice on doing some of this stuff. And I want to just go through this one more slide and then we'll kind of wrap things up for today. So we've spent a lot of time talking about intermolecular forces today. We talked about intramolecular forces, so that's intra, remember, is the forces that are involved in the chemical bonds within the molecule. And then we talked about intermolecular forces, whether it be the dispersion forces or dipole-dipole, hydrogen bonding, things like that. And that's the intermolecular forces, which is one molecule interacting with another molecule. Those interactions aren't as strong as the intramolecular bonding forces, but they do really impact these physical properties. And so here we have a list of liquid properties. So we're just talking about liquids now, and how that are affected by intermolecular forces. And so boiling point, we've talked about that quite a bit today, but it also holds true for melting point, okay? Viscosity, does anyone know what viscosity is? Viscosity is kind of, think of it as thickness. So like syrup is much more viscous than water. So syrup pours more slowly. Or sometimes people will use motor oils as examples. Those ratings on the motor oil really is the viscosity. So it's the thickness is really what it's telling you. So we'll talk about viscosity a little bit. Surface tension, capillary action are two others that are used to describe liquids, and we'll talk about what those mean and what they are, and show once again how these intermolecular forces impact the materials, boiling point, melting point, viscosity, surface tension, capillary action. And so it's kind of interesting that the bonds aren't what's really impacting it. The strengths of those is the strength of these molecules interacting with each other through these dispersion forces, van der Waals type things, hydrogen bonding, stuff like that. So we're going to wrap up for today. Any questions before we end? Okay, thank you.